Everyone, and welcome. Today we're diving into something that is, and I mean this, genuinely groundbreaking. We're talking about a new technology that's giving scientists a front row seat to one of the biggest mysteries in medicine. What happens in the very first moments of a stroke?
You know, for everything we understand about strokes, this has always been the central question, right? What is actually going on in that hyperacute phase, right at the very beginning? That single moment can determine everything about the damage and the potential for recovery, and yet it's been almost impossible to see.
And that's why scientists have this name for it, the black box. Think about it. By the time a person feels symptoms, calls for help, gets to a hospital, and is finally put into a scanner, those crucial first minutes or even hours are long gone. Whatever happened in the brain at the start, it's remained a total mystery.
All right, so let's dig into that. Why has this black box been so stubbornly locked for so long? So, just to be clear, we're focusing on ischemic strokes here. These are by far the most common kind, making up about 87% of all cases. It's when a blood vessel in the brain gets blocked and brain tissue starts being starved of oxygen. So yeah, understanding how that whole process kicks off is absolutely critical. So what's been stopping us? It really comes down to three big problems. First, as we said, the time delay. It's just too long. Second, the tools themselves were an issue. A lot of the existing models for studying this in animals use things like metal coils, which are a total non-starter if you want to use an MRI. And finally, there was no on-off switch. Scientists just couldn't start, stop, or even reverse a blockage in a controlled way to really study it properly. Well, until now.
And that brings us to the solution. An absolutely incredible little piece of microengineering that's basically the key to finally unlocking that black box.
So say hello to the microballoon. This thing is tiny, smaller than a millimeter. It's completely MRI safe because it's made entirely of polymers, and it can be controlled from a distance with just incredible precision. It's basically designed to go into the tiniest arteries and gently squeeze them, letting researchers dial blood flow up or down whenever they want for as long as they want.
Okay, so take a look at this, because it really puts into perspective what a huge leap forward we're talking about. The old tools, not safe for an MRI. The control, it was either on or off and usually permanent. But this new microballoon, it checks all the boxes. It's safe, you can fine-tune the blockage, and, this is key, it's completely reversible. We are talking about a whole new class of tool for neuroscience.
So you're probably wondering, how in the world do you build something that tiny and that precise? Well, the engineering story behind it is just as cool as the science it's enabling.
It's all about some really clever micro-manufacturing, almost like 3D printing on a tiny scale. They start with a tiny mold. Then they coat the inside with a super flexible silicone layer using a little jet of air. After that, they add a much stiffer polymer in specific spots to act as a frame. A final flash of UV light hardens everything, and boom, you have this incredibly sophisticated little device.
But here's the real magic, the secret sauce, if you will. It's all about how these two different materials work together. You've got the soft, stretchy silicone that forms the balloon part. It wants to inflate in all directions. But it's held in check by that super stiff PUA, which acts like a rigid frame, forcing the balloon to expand in a very specific and predictable way. It's brilliant.
And we're not talking about a small difference here. It's huge. That rigid PUA frame is about 60 times stiffer than the soft silicone part. And it's that massive difference in stiffness that gives researchers such fine-tuned, predictable control over the squeeze.
All right, so they built this incredible tool. The big question is, what did they see with it? For the very first time, they could actually watch the stroke start, in real time and in incredible detail.
So when they fully inflate the balloon in the artery of a mouse, they see a staggering 96.5% drop in blood flow to the brain. What that means is they can now reliably create the exact conditions of a severe stroke on demand.
But the really cool part is that it's not just an on-off switch. It's more like a dimmer switch. As you can see here, they can leave the artery wide open, or they can partially inflate the balloon to reduce blood flow by a little, or they can block it almost completely. This tunability is a game changer for studying all kinds of different scenarios.
So, what was hiding inside that black box? Well, one of the first big discoveries was something they called a rapid vasoconstrictive response. Basically, as soon as they cut off the blood flow, the blood vessels themselves squeeze shut. This is a dynamic reaction that could be making a bad situation even worse, and it's something that was basically impossible to observe before now.
Okay, let's actually look at what this looks like inside an MRI scan. Here's our baseline. This is a healthy brain with normal blood perfusion. You can see blood is flowing nice and evenly across both sides of the brain. Everything looks good.
And then they inflate the balloon. And instantly, the picture just changes completely. The MRI captures this huge drop in blood flow to the targeted areas. This is it. For the very first time, we are watching an ischemic event unfold, live as it's happening.
Okay, so this is obviously a massive deal for researchers. But let's zoom out. What does this actually mean for the future of medicine? Why should you and I care about this?
So, if we boil it all down, what are the huge breakthroughs here? First, it finally unlocks that black box, letting us see the start of a stroke with real-time MRI. Second, the precise and reversible control means scientists can now model everything from a major stroke to a minor transient attack and even study the recovery process. And maybe most importantly, it's already revealing these hidden biological responses we never even knew were there.
And believe it or not, this isn't just about stroke research. The potential here is so much bigger. You could adapt this kind of technology to study other blood vessel diseases, like in the heart or legs. You could even use it to better understand how things like our digestive system work. This could be the key to a whole new generation of therapies.
And that leaves us with a really powerful question to think about. For so long, those first few minutes of a stroke have been a complete mystery. Now that we can finally pull back the curtain and watch it all happen, moment by moment, what secrets are we going to uncover? And what life-saving treatments are just around the corner? The black box is finally open.